Now let's talk about tree. So what is tree? So before we start tree, let's first understand what are the different type of data structure. So I'll not go much in detail about data structure, what is data structure and all those. You may read yourself. So DS broadly it is categorized into two. One is linear data structure and another is non-linear data structure. In linear data structure, you must have come across about arrays, linked list. Okay. So tree is an abstract data type. Tree is an abstract data type. Some textbook says it is an abstract data type, which is correct. This may be conceptual and might not be concrete if you don't have prior knowledge of underlying data structure. If you have prior knowledge of data structure, that this tree is implemented using the data structure array or using the data structure linked list. Again, with the same case, linked list is also ADT. Linked list is also an ADT. But for the moment, consider it as a data structure. So if you know the underlying implementation is array or linked list, then you can say tree is a also data structure, which is categorized in non-linear data structure. Okay, you may read more about this abstract data type. Okay, so let's see what are the different type of trees. Okay, suppose I have a node which we always call it as root, and it has at most two children, left children and right children. At most, it means it could have only one children also, only one child also. Either it may left or right, or it may have no child at all. So this is also a tree. So what is the definition of tree? A tree is a non-linear data structure, which do not have any cycle in it. Okay, and it may or may not have any children. Okay, so this is a tree with one node. Some textbook also suggest that if you have no node, then it is also called as an empty tree. So if you have no node, why would we call it as an empty tree? I don't understand. Okay, so I assume it must have a root and it may or may not have any children. Okay, if we talk about binary tree, the tree could have at most two child. At most two child. Now let's see how we can implement this tree in using array data structure. suppose this is my tree. Suppose this is my tree. So when we use underlying data structure array to implement this tree, remember, for any node I, the left child is denoted by, is indexed at, if any node is indexed at I, the left child is indexed at 2i plus 1, and the right child is indexed at 2i plus 2. And if any node I is given, the parent of this node I will be I by 2 ceiling function. Okay, so what is parent, what is child, these term, let us see first these term. So this is called root. B and C are children of root A. D and E are children of node B. D, E, F are leaves. Since there are no children in it, if any node whose child is not present, both child is not present, that node is considered as leaves. Okay. If this is parent of this B and B is a parent of D, then D is grandchildren of node A and A is grandparent of node D. Now A is ancestor of D and D is descendant of A, right? Now we will see for any node I. So what is I? I is the index in this array. So in this array, okay, this is index 0, 1, 2, 3, 4, 5, 6, 7. So the root is always at index 0. So root is at index. So if you have to implement this tree, you can use this data structure to implement this tree. So you place this root at index 0. Thereafter, left child will be placed at 2i plus 1 for any node I. So if this node is I, the left child will be at index 2i plus 1. So if this is at 0th index, 2 into 0 plus 1, that is 1, will be the index of the left child. So B will be placed at index 1. For right child, we will compute 2i plus 2. So I is 0, 2i plus 2 is 2, which is the index for this element, this node, which is C. Fine. Now what is the index value of this D element? We will see the parent. Parent is index at 1. So the left children will be 2 into 1 plus 1. As per the formula, 2 into 1 plus 1 is 3. So D will be placed at 3. Similarly, E will be placed at 4. Now suppose if you ask, what if this node is not present? What if this node is not present? So the index for the right child of this B must be present at index 4. Since the child is not present here, we will mark this as an empty. Else, if you do not mark this as an empty and you put F here, and when you retrieve tree from this array, you would assume that this index 4 is the element which is at index 4, which is F, is the child of this B. So for that we will mark dash here. Now for C, 2 into 2 plus 1, which is 5. So F will be placed here. Okay. So you will ask, what about this size? That depends upon how you are implementing your tree. If this is user input tree, then you have to take an array and then you have to grow it twice, which is another topic, we will discuss it later. So you need to have some size of this array, okay, some bounded array. Now how to compute the parent for any node I? Suppose I have this element C, which is index at 2, which is index at 2. So this is I minus 1 upon 2. This is floor function, okay. So we need to compute this. We need to compute the parent of this C element. So what will be the parent? 2 minus 1 upon 2, which is 0. So this is the parent of C. If we compute the parent of B, 1 minus 1 upon 2, which is 0. So A is the parent of B. Okay. So now next we will see what is height. So what is full binary tree? Full binary tree is also known as two tree. What is two tree? So a full binary tree means for each of the node, either it has no children at all, or if it has children, it will be exactly 2. So if this is a node, it should have exactly 2 children. And if this is a node, it may have exactly 2 children, or it may have 0 children at all. So it has no children, it has no children, satisfied. It has 2 children, satisfied the property. So this is full binary tree. What about this? This is also full binary tree. Since this node has exactly 2 children, and this node and this node and this node has exactly no children. What about this one? This is not full binary tree. Why? Because this node has only one child, and the definition is either 2 child or no child. Now what about complete binary tree? What do you mean by complete binary tree? So you should remember a tree whose every level is filled. A tree whose every level is filled except the last one, and if the last one is filled, it should be as left as possible. The nodes should be as left as possible. So if this is a tree, this level is filled since there are only one node here. This level is also filled since both are present. This level is the last level, and in the last level both this node is as left as possible. What about this? This is the last level. This is 0, 1 and 2. This is the last level, and this last level, if you see, it is not left. These two nodes should present this side. Okay, so that was not full binary tree, and this is complete binary tree. Now what about this one? This is also not complete binary tree. This is not complete binary tree. Why? Since at last level this node should be as left as possible. Okay, so what is full complete binary tree? In complete full binary tree, the full binary tree suggests all the children must have either 0 or 2 child, and complete binary says the last level should be as left as possible. So this is full and complete also. This is neither full nor complete. This is full and complete also. This is also full and complete. This is complete. This is full but not complete. Why? Because it is full since this node has no children at all. This has 2. This has also 2. Why it is not complete? Because it is right oriented. It should be left oriented. Okay. Now let's talk about the height. So this is at height 0, this is 1 and so on. This is h. So you must be thinking why the height is going downward. Basically the tree concept starts from root. So root is here and it grows like this. So these are the leaves. So when we say this is level 0, this is level 1, this is level 2, and so this is height 0, this is height 1, this is height 2, and depth, if you count, depth count from this side onward. So this is 0 depth, this is 1, and this is depth 2. So height and depth of any tree is the same. So basically root starts from the bottom and it grows up, but we represent this tree in this manner. Okay, so it is upside. Okay, the root is upside. Now in this case, if you see, what is the total number of element at height 0? What is the total number of element is at height 0? It is 2 raised to power 0. 2 raised to power 0. What is the number of element at level 1? It is 2 raised to power 1. What is the number of element at level 2? Level 2. It is whatever the previous total element, each element has 2 more children. So this 2 raised to power 1 was the previous node, and we multiplied each of these 2 raised to power 1 by 2, assuming it has 2 children, and so on. Assume that it is at height h, that level h, and it is full complete binary tree. So this is 2 raised to power h. So what is the total number of element here? This is geometric progression. If you do the computation, it will be 2 raised to power h plus 1 minus 1 upon 2 minus 1. Okay. So this is the total number of node at max it can have in this tree. So if a tree has height h, it will have a maximum of these many nodes. So I assume that there could be number of node which can be less than this also, or equal to, right? So what I am trying to compute here, I am trying to compute this height h. So what will be the height h? 2 raised to power h plus 1 is equals to n plus 1. Okay. Height is what? Log 2 n plus 1 upon 2 raised to power h 2 divided by 2. Yes, this is height. So we can say the height of any tree is in the order of log of n. So if you have n element in the tree, the height will be order of log n, right? Now what is the total number of node in the leaf? What is the total number of node in the leaf? In the leaf, total number of node is 2 raised to power h. Total number of leaves is 2 raised to power h. And what is the total number of element in the internal node? In the internal node, the total number of element will be 2 raised to power 1 plus 2 raised to power 1, so 2 raised to power 0, 1 till 2 raised to power h minus 1. So let us first compute total number of leaves. So we have the formula here, n is equals to 2 raised to power h plus 1 minus 1. We can write it as, fine. So total number of leaves is what? N plus 1 by 2. Okay. What was the total number of element in the entire tree? It was n. What was the total number of element in the leaf? It was n plus 1 by 2, which is what? This is internal node. I would call it as I. The total number of element in the internal node is 2n minus n minus 1 upon 2, which is n minus 1 upon 2, right? So I can write total number of leaves is equals to total number of internal node plus 1 also. If you see, if you add 1 here plus 1, so it will be n plus 1 by 2, which is I plus 1. So total number of leaves will be total internal node plus 1. Plus 1. You have to remember this. Now let's talk about minimum height of a tree and the maximum height of a tree. So suppose in a tree you have n node. What will be the maximum height the tree can achieve? Okay, fine. I have node 1 here, node 2, node 3, node 4, so on node n. So this will be what? Height 0, this is height 1, this is height n minus 1. So maximum height of any binary tree with total number of node n will be n minus 1. What about the minimum height? Minimum height will be when it is full and complete. When it is full and complete, which is at left side. So minimum of height of any tree, maximum height, minimum height of any tree with n node will be what? At least this much height. Log of 2 n plus 1 upon 2. This may also be written. What was n plus 1 by 2? N plus 1 by 2 was total number of leaves. So minimum height will be number of leaves upon 2. Or you may also write log of 2, log of internal node plus 1, log 2 of internal node plus 1. Fine. You may also ask, the tree could be in this fashion also. Yeah, you may have any option. At each stage you have option, either you can go left or right, but you must ensure that for each of the child, for each of this node, there will be at max only one child. Okay, so that possibility could be 2 raised to power 0, 2, 2, 2. So you may compute how many different tree can be produced.